In this video, we will see in Physics for Electronics Engineering Unit 1 Electrical Properties of Materials. Initially, we will start with the electron theory of metals. Aims to explain the structures and properties of solids through their electronic structure, and it explains valence electrons present in valence band and which is responsible for various properties of metals. Conducting materials are defined on the basis of their electrical and thermal conductivity. It has developed in three stages: the classical free electron theory, otherwise known as macroscopic theory; the quantum free electron theory, otherwise known as microscopic theory; the zone theory or band theory or Brillouin theory. Classical free electron theory. In 1900, Drude and Lawrence developed this theory, which assumes that metals contain free electrons, obeying the laws of classical mechanics. In this theory, the free electrons in metals are assumed to move in a constant potential. The quantum free electron theory or microscopic theory. Sommerfeld developed this theory during 1928, in which the free electrons obey the quantum laws. In this theory, the free electrons are assumed to move in a constant potential, and the Fermi level electrons are responsible for the properties of metals. Band theory or Brillouin theory or zone theory. Blas stated this theory in the year of 1928, in which the electrons move in a periodic potential provided by the lattice. This theory also explained the mechanism of semiconductivity based on band, hence it's named as band theory. Drude-Lawrence theory or classical free electron theory. First theory to explain the electrical conduction in conduction materials. Drude and Lawrence proposed this theory in the year of 1900. Free electrons are fully responsible for electrical conduction. Usually in an atom, central nucleus with positive charge surrounded by the electrons of negative charge. Drude assumed that the electrons in a metal are free to move in all the directions and form an electron gas. These free electrons move like the gas molecules in a container. So it obeys kinetic theory of gases. The concentration of free electrons is 10 power 28 meter per minus 3. Postulates. In an atom, electron revolve on the nucleus. The valence electrons of atoms are free to move about the whole volume of metals like the molecules of a perfect gas in a container. In the absence of electric field, these free electrons move in random directions and collide with each other, and all the collisions are perfectly elastic. Since the electrons are assumed to be perfect gas, they obey the laws of classical kinetic theory of gases. Also, the electron velocities in a metal obey the classical Maxwell-Boltzmann distribution of velocities. When an electric field is applied to the metal, the free electrons are accelerated in the direction opposite to the direction of applied electric field. Drift velocity. The average velocity acquired by the free electron in a particular direction due to the application of electric field is said to be drift velocity. Vd equivalent to L by tau. Relaxation time. It is the time taken by the free electron to reach its equilibrium position from its disturbed position in the presence of applied field. In other words, it is the measure of time that the electrons can relax when the electric field is removed. It is approximately equal to 10 power minus 14 seconds. Tau is equal to L by Vd. Mobility. Mobility of an electron is defined as the drift velocity acquired by an electron per unit electric field applied to it. Mobility mu is equal to Vd by E meter squared world power minus 1 second power minus 1. Collision time. It is the average time taken by the free electron between two successive collisions. Tau z equivalent to lambda divided by Vd, where lambda is a mean free path. For an isotropic solid like tau z equivalent to tau, mean free path lambda The average distance traveled between two successive collisions is called mean free path. Lambda equivalent to c bar into tau c, where tau c is the root mean square velocity of the electron. Thank you.